and everything. It's just your typical quiz, but I think it is going to be like through like the Proctorio settings.
Okay, thank you.
You're welcome.
Good morning, Phoebe. Are you going to be posting your practice exam this weekend? Well, today?
Yeah, so I was going to discuss that, but I might as well just say something now about it. I actually finished it like 2 nights ago. I sent it to Dr. Patel because all the professors have to like review the questions. I sent it to her yesterday, like around noon, and I'm just waiting for her to give me the go ahead before I can post it. So hopefully that's by the end of the day, hopefully sooner rather than later, though.
Okay, thank you.
You're welcome. All right, guys, it's 9 o'clock, so I'm going to go ahead and start. There's a few things that I do want to talk about that I didn't already just talk about before we do start, so I'm going to discuss those now. Like I said, we have the Q&A session today again, as usual on Fridays, and you'll expect 12 questions from me for this week's material. And I also have your practice exam. I'll post it whenever I get permission to do so. Okay, so I did talk to Dr. Patel a few days ago regarding some of the questions you guys had asked me about, like general test questions. So the first question that I talked to her about was whether there's going to be pictures on the exam. So she said, yes, there's going to be a picture on the exam. And she specifically said that it's going to be a graph and it's going to be regarding enzyme kinetics. So right away, I can tell you it's probably either going to be the Michaelis-Menten plot or the Lineweaver-Burke plot. And you will likely have to determine whether a competitive or non-competitive inhibitor has been added to it. So make sure you can read those plots because she is going to ask about it. Another question I got was whether like the math was going to be kind of difficult because I know you guys don't have a scrap sheet of paper and that the Proctorio little whiteboard thing is trash. So what I got from her was that she and Ferreira both removed all of the heavy math questions this year because they realized that it's going to be hard to like do the algebra when you don't have scrap paper. So what she did say, however, is that she will have like easy math. And she described this easy math as like A plus B equals C. So if you're not like a mental math person, it might be a little bit more difficult because this is like, it's still going to have some kind of math in it. What I would suggest is, I know that Proctorio's little whiteboard thing, like, you can't really write on it because it doesn't work very well, but you can still type on it. So if you need to see the numbers, I suggest using your keyboard, the like function and typing the numbers so you can kind of see what you're doing. That's my best suggestion. Hopefully the math is like super simple. I know last year she kind of gave you the values for like the logarithm and all of that in the test. It was like way easier than I thought it was going to be, but it was a little bit tricky. So I'll warn you guys that she will give you the values of the logarithm. So she'll give you your pK values, and this is for the Henderson-Hasselbalch equation. She'll give you your pK value, your pH value, and then like ask you to solve for one of those. And last year she gave us like log of base over acid equals, she put like 10 or something like that. And then a lot of us misread the question, myself included, and found the log of the log value she already gave us. So we got the answer wrong. So make sure not to make that mistake. I did want to like say that. But because she did that, she made the math way easier for us. So hopefully she'll do the same for you guys. Because I really don't remember there being a whole lot of math on the first test. Okay. And the last thing she wanted me to discuss with you guys was she specifically noticed last year and the years before that many people were having trouble with the exam because they would second guess themselves. So she specifically wanted me to tell you guys not to second guess yourself, and that when you're going through the exam, only ever change your answer on a question if you misread the question the first time. So typically what I do when I go through the test, because taking the test is like half the battle of doing well. Like you can understand everything, but if you're misinterpreting the questions or not answering what is being asked, you're not going to do that great. So what I suggest is when you first open up the exam, you answer all of the easy questions first, and that way you can kind of refamiliarize yourself with the material. It's kind of like a warm up, and then you also kind of build your confidence in understanding the material by doing the easy questions first. Then I typically go back and I do the harder questions or the time-consuming questions, like the math questions I would do second. And then after that, I would review the test one last time and kind of reread every question and answer to make sure that I'm selecting the right answer. But when I'm doing this, I don't recommend changing your answer unless you read the question wrong the first time. So try to avoid doing that. And, with the practice quizzes, I would suggest like practicing not doing that if you know you're the type of person who tends to do that. So lastly, I did want to let you guys know that I'll be holding office hours probably Sunday late afternoon, and then again on Monday. So for Sunday, it's like more catered towards people who have any questions about like the practice exam or, just general questions. And then Monday morning, I'll also be available for any like last minute questions for anybody who's like, just figuring out something like at the last second. So hopefully that works for you guys, and it'll be through Teams, obviously. So something that I found useful before like taking the exams that I kind of made a habit of is meeting with my study group every morning, and we would quiz each other. So that way you're like kind of, doing the whole active recall thing and like talking about it with your group members. If there's something that you didn't quite understand, you can like realize that you don't understand it when you're talking about it with other people. And then a lot of the times, like my study group members would give me like a really easy way of remembering something if I'm having trouble remembering it. And it has saved me a lot of times while I'm taking the exam. So I suggest doing that. So yeah, if you don't have a study group and you're like interested in that sort of thing, I don't mind, doing that Monday morning if there's not a lot of questions. So just let me know. I think that's all I wanted to talk to you guys about. Does anyone have any questions about anything that I just discussed?
Hey, Phoebe.
Yeah.
Would you say that your one-page notes, like on Canvas, like are the more high-yield material that we should like try to memorize and focus on, or that like it's probably just like equal to everything else in the PowerPoint, but that you just kind of just like made a one-page note for those things specifically?
So what I focused on those one-page notes are the high-yield information. But, I mean, the professors can ask about literally anything. I feel like Patel and Ferreira tend to stick to the main information, but sometimes you'll see like a question on like smaller details. Additionally, I recommend memorizing the little details because every once in a while they'll use like details as some of the answer choices. They may not be the right answer choice, but if you're stuck on a question, knowing the details can help you narrow it down by looking at the other possible answer choices. And if you understand this small detail and it's not right, to like cross it off. So I mean, I recommend it. But for the most part, I would say the high yield points were on my papers.
Thank you.
You're welcome.
Hi,
Anything
Phoebe.
else? Yeah.
I have a question. I know about the pictures on the exam. I know you asked Dr. Patel and she said there be a picture. Um, how about Dr. Ferrer? Are there going to be any pictures on her section of the exam?
So, I mean, from what I remember from last year, there weren't any like pictures that like, if you were looking at like a protein structure, anything like, a drawing of any kind. It was like usually almost always a graph. For biochemistry, at least. That's not to say that for genetics, you're not going to have pictures because you will. But for biochem, I just remember the first test having just a graph and no other kind of detailed questions. As for whether Ferreira will have a graph on hers, I mean, I feel like Dr. Patel, because Dr. Patel's the one who reviews the test before, they put it out there. So she would have probably told me about it. But I feel like Dr. Ferreira's material didn't have a whole lot of graphs that she would likely test on. But I think it's, best to understand all of the graphs because that also helps you understand the concepts better. So, yeah, that's like as the best answer I could give you for that.
All right, thank you.
You're welcome.
Hey, Phoebe, for the graph that you said she was probably going to use, what do we need to know what would we need to know was added to it?
Like whether a non-competitive inhibitor or a competitive inhibitor, because that would change the X and Y intercept on the Lineweaver-Burke at least. Because the Vmax would change, or the Km would change, and then, you would have to determine like which was added based on what you're looking at.
Cool, thank you.
You're welcome. Anything else? Okay, there's no more questions. I'm going to start the, lecture. Okay, can everybody see my screen?
Yes.
Thank you. Cool. Okay. So I feel like enzyme kinetics is probably one of the harder topics for biochem. So yeah, hopefully I can explain this better. Okay, so this first slide, she's just kind of reiterating everything she said during the first lecture, or the last lecture, which was just the enzymes, just basically that they bind temporarily, they bind to substrates, they lower the energy of activation, and then they speed up the reaction. They're selective, and then they're specific, and it's pretty much just a summary of everything you learned from the last lecture. And then she goes on to introduce the two types of reactions. So I think it's important to understand the difference between the kinetics and thermodynamics. Remember that enzymes do not deal with thermodynamics. They only deal with kinetics, which is really just the rate of the chemical reactions. So she starts off by introducing a zero-order reaction. So in this kind of reaction, you'll see that the rate of the reactant decreasing is constant. So there is no change in the slope. It's a constant line. And then the product, because as you turn substrate into product, it's going to go at the same exact rate, but it's going to increase instead of decrease. So this is just plotting the concentration of each of these over time, and they're pretty much proportional, but opposite to each other. So this is showing you the same exact thing, but specifically, I believe, just the substrate. So you'll see that the substrate would decrease over time, and the slope is kind of just constant. So that tells you that the velocity of this is constant. And then this is just showing you the derivative of it. So the derivative, if you remember from calculus, is really just the slope of a point on the line. When you take the derivative of a straight line like this, it will show something like this. It's got a zero slope. So because there's no slope, you know that the rate of the reaction is not changing. So what I would take away from this is this formula right here. You've got your constant, which is going to be based on the individual properties of the enzyme. So things like how well it attracts the substrate and how fast it can cause the reaction to progress. And then this is just your concentration of substrate. And because it's to the zero power, you know that anything to the zero power is going to be 1. So you know that the rate is only going to be proportional to the constant. And that's, going to allow it to be independent of the amount of substrate added. So you can add as much substrate as you want, but the reaction is going to progress at the same rate. So the next thing she introduced was the first order reactions. So these are different in that they're what are these called? Hyperbolic curves. So you'll see that the slope at different points along the line is going to be different. Specifically, you'll see that the slope at the beginning of the line will be steeper than the slope at the end of the line, and eventually it flattens out. So that's how you know that the reaction rate is starting to decrease as it goes, as it progresses over time. So remember, this is just plotting the concentration of the product over time, and that it decreases over time. So same formula here, I would remember this, is that the velocity of the reaction is going to be proportional to the amount of substrate, meaning that if you add more substrate, it's going to increase the velocity proportional to the amount that's added. So know this formula and understand this kind of relationship. So I would also kind of keep in mind that the initial velocity is going to be the fastest velocity. So this is going to have the steepest slope when you take the derivative of it. So you know that's going to be the fastest velocity during the reaction. And when it flattens out, when it's plotted from between concentration and time, when it flattens out, this is when it will reach equilibrium. So you'll have equal amounts of reactants and products. So your velocity of the reaction is not going to change. So don't get that confused with the Michaelis-Menten plot, because that, when it flattens out, it's going to show you something different. Okay, so this is putting those two together. You have your constant, you've got your substrate, you've got your product, and then you've got your order of the reaction, whether it's a 0 order or a first order. And then it's pretty much saying that for, enzymatic studies, you need to have a lot of substrate versus a smaller amount of enzyme. And that's really just so you can measure it better, because if you don't have, if you have like equal amounts of substrate and enzyme, you're not going to be able to measure the kinetics as well as you would with smaller enzyme and larger substrate, which is more consistent with the physiological concentrations of each. Additionally, when you get too much substrate, so at some point you're going to increase the substrate so much that it's going to saturate the enzyme, and at that point you're going to have your 0 order reaction because the velocity is not going to change with an increase in concentration. So she was just kind of introducing the fact that with enzyme kinetics, most enzymes will be first order at the beginning and then 0 order towards the end when they reach their maximum velocity and the enzyme is saturated. So I would also know that the enzyme is not considered a reactant because it's not being used up. It is known as a pseudo-reactant, and it just really helps the reaction progress. I would also know that when you're plotting the reaction velocity, so this is your Michaelis-Menten plot, to the substrate concentration, it's going to form a hyperbolic curve. So when you reach Vmax, your enzyme is saturated and it can't increase the velocity of the reaction because it doesn't have any more enzyme to help move it along faster. But when the substrate concentration is low, you're going to see that it's going to follow a first order reaction rate because it's going to increase with an increase in concentration added. So this is once again just plotting the product to time at different substrate concentrations. So this is essentially how they will ultimately plot the Michaelis-Menten plot based on measuring the substrate concentrations at the velocity at different concentrations of substrate. So what they do is they have like a solid amount of substrate at one concentration. They measure the reaction. Remember that the initial velocity is going to be the fastest velocity. So they take note of the initial velocity and they use that to plot the Michaelis-Menten plot. And they do it for each of these different substrate concentrations. And so you need to know that the initial velocity is what's being plotted in a Michaelis-Menten plot because it's the fastest velocity during each of these reactions. So for this, she's kind of introducing the idea of steady state assumption. I would say that the steady state assumption is pretty high yield. So essentially, your reaction is going to start off with an enzyme and a substrate, and then it'll combine to become the enzyme substrate complex, which then becomes product, and the product is released from the enzyme, so they become two separate entities again. So this constant here is pretty much based on the properties of the enzyme and is kind of based on how fast the enzyme can take up the substrate to become the enzyme substrate complex. The K2 value is going to show you how fast the enzyme can convert the substrate to product. So I would know that the K1 is typically very fast because it doesn't take a whole lot of time to just move the enzyme and combine it with the substrate. On the other hand, the K2 is slower because it takes more time to convert the substrate into product. And so I would know that this is the limiting rate for this whole sequence of events. So the K negative one is going to be, occur when this enzyme substrate complex dissociates back into enzyme and substrate, and that tends to happen sometimes. So I would understand that. There does exist a K negative too, but because, this happens so rarely, they kind of make it equal to 0, so they don't really talk about it. But yeah, the steady state assumption is assuming that the rate of putting these two together is going to be equal to the rate of dishing out products. So you'll see that the amount of enzymes that are combined with substrate is going to be pretty steady as the reaction progresses. So that's, like I said, based on the rate of association being equal to the rate of dissociation, which is also going to take into account the fact that sometimes the ES goes back to being just E and then just S. So the steady state assumption is important for being able to derive the formula for the Michaelis-Menten plot, which you will see now. Okay. So this is going to be your Michaelis-Menten constant. So I would memorize this formula here, but pretty much what it's saying is that this is your your constant associated with the formation of this enzyme substrate complex. So it's shown right here. And then these two are going to be associated with the dissociation of the complex. So either it becomes enzyme and product or it becomes enzyme and substrate again. So it's associated with the dissociation. So essentially what Km is showing you is that it's equal to the breakdown of the complex over the putting it together. So if you put it to, you have the breakdown constant over the association constant, so putting it back together, you're going to have a number that's going to tell you essentially the affinity of the enzyme for the substrate. If the breakdown is a greater number than the association of it when you're putting it together, then you know that you're going to have a Km value that is going to be greater than 1. And so it's going to be a high number. And that's going to tell you that because it's breaking down more frequently than it's coming together, you're going to have a low affinity for the substrate. On the other hand, if you are going to be putting it together more so than you're breaking it down, that's going to tell you that's going to be a fraction because the denominator is going to be greater than the numerator. So now your Km is going to be less than 1, and that's going to show you that it has a higher affinity for the substrate. And so they use this kind of assumption to kind of create this formula, which then they use to go on and create the Michaelis-Menten equation, which you don't have to know how to derive. So yeah, this is your Michaelis-Menten equation, same kind of thing. And they use the steady state assumption that we just talked about to kind of derive it as well. I would know this formula. I would understand how it's plotted on a graph, which we'll get into. But yeah, definitely memorize this formula. She also talks about the Kcat, which is the catalytic rate. So this is pretty much telling you how fast a enzyme can dish out products. So it's the sequence of events where, it takes in the substrate, converts it to product, releases the product. So this is going to tell you a little bit about how efficient the enzyme is, along with the Km. So having a low Km, like we just talked about, means it has a high affinity, means that it likely has a better efficiency. Having a high Kcat means that it has a high turnover rate, so it can dish out product a lot better. And therefore, you know that you're going to have a high efficiency as well.
Hey, Phoebe.
Yeah.
For a steady state, basically does that just mean that like the enzyme substrate like complex, that's just showing that like the graph is showing that it's steady over time because the enzyme like favors the substrate?
Sort of. Like, it's pretty much saying that the rate of putting it together is equal to the rate of breakdown. So if you have 10 of these coming together at the same time as 10 of products being released, you're not changing the concentration of ES because, build up equals breakdown. Does that make sense?
Okay, yeah, that makes more sense. Thank you.
No problem. Oh, sorry, Elizabeth. I just realized that you typed some things in the chat. So, wow, this is like from a while ago. Okay, so I'll be posting my office hours for Sunday and Monday, probably later today. And office hours will be on Teams, and we can discuss the practice exam Monday morning if you would like as well. Okay, and then Abigail, what is efficiency in this context? What do you mean by that? So like, Kcat gives you a hint as to what the efficiency is based on the turnover number. So if it's really good at dishing out product, then it's highly efficient. Km tells you the affinity. So if it has a high affinity for a substrate, that means it attracts substrate better. And that also kind of gives it better affinity. I'm not sure if I answered your question, but okay. Yeah, so I mean, it could mean that it's a faster, but essentially what it means is that the rate is faster because it's better at grabbing the product, grabbing the substrate, turning it into product and dishing it out. So essentially it's going to work better and faster. So yeah, both affinity and the ability to convert it into product they're both going to play a role in the efficiency of the enzyme. So how efficient it is at converting product and making product. Okay, so the Michaelis-Menten equation that we talked about can be plotted on a graph. And so this would be your Michaelis-Menten plot. So essentially, and don't confuse this with the plot of the concentration that we saw earlier. The last graph or a couple graphs ago, we saw that this was the y-axis was the concentration and then the x-axis was time. So don't confuse that here because in that scenario, your flattened out curve would be equal to the equilibrium of the reaction. But in this case, this is more important, you're essentially taking all the initial velocities from those graphs and plotting them to their substrate concentration. So each change in substrate concentration will have a change in the initial velocity. So as you go along, you'll see that the rate is going to decrease and it's going to flatten out the curve, ultimately leading to the arrival of Vmax, which is the maximum velocity or the maximum initial velocity for each of these enzymes at a different substrate concentration. And so that's as fast as the velocity can go because the enzymes are now saturated. So when you take the half of that, which is Vmax over 2, you're going to be able to plot the Km, which is going to tell you about the affinity of the enzyme on the x-axis here. So Km is essentially equal to half Vmax when you plot it on the Michaelis-Menten plot. So if you, like I said earlier, if you have a smaller Km, you know that your buildup is going to be faster than your breakdown because it's going to be like a fraction number. So you know that your enzyme is going to be more efficient. So that's why you want a low Km on this graph. If I were to kind of show you the addition of like one of the types of inhibitors, and you'll see if you see that the Km changes, you're going to know that you're now looking at a competitive inhibitor, because the competitive inhibitor is going to cause cause a decrease in the affinity for the substrate. But we'll get to that. So yeah, I would understand that Km is equal to half Vmax, and understand that it also determines like the affinity of the enzyme for substrate, and that you want a lower Km for it to be a higher affinity for substrate. Yeah, okay. So when you're looking at the Lineweaver-Burke plot, I would know, this equation here, it's essentially your typical y equals mx plus b linear equation. So you know that the b is going to stand for the y-intercept, which is here. You see that's the y-intercept. And then this is going to determine your slope, because that's what m stands for. So I would understand how this formula relates to the graph, and how it would change the graph with a change in either Km or Vmax. So yeah. So this slide is pretty much showing you how how it's all determined in a lab setting, how they can essentially prove the Michaelis-Menten equation kinetics is, what works. So you don't have to know like the details of this, maybe just knowing like the general steps associated with it. But I would say it's pretty low yield. But essentially what they do is they take, a solution, they add different concentrations in each of these of substrate. So you'll have an increasing substrate concentration for each of these. Then they will, for each of these, try to determine the amount of product being made. And so that's how you can kind of determine the amount of product formation, and ultimately determine the initial rate of the reaction. So now they'll plot these changes on a graph. So remember, this is your product over time. And they'll essentially find the V0s for each of these, which is, remember, the fastest rate. And they'll then plot the V0s on the graph with their substrate concentration that they're associated with. And this is how you'll get your Michaelis-Menten plot. So I would say this plot is definitely more high yield than understanding this plot. So don't worry about this too much, but just don't get the two confused. Okay. So same thing here. This is just showing you that you would do this experiment with an increase in substrate in each of these little test tubes, and then you would plot their initial velocities for each. So this would be an initial velocity, this would be an initial velocity. Leah, can you go over Lineweaver-Burke again? Yeah, I can go over Lineweaver-Burke again. Where was that? Okay. So this is your linear equation. This is your y, which is equal to 1 over v here. So your y-axis, your x-axis is equal to 1 over s. So this is your x-axis. And then your Km over Vmax is going to be what your slope is. So you'll see that when you add a competitive or non-competitive inhibitor, because each of these changes either one of these, the slope is going to change with both. With the y-intercept, if your Km changes, then, I'm sorry, your x-intercept. Your x-intercept, if your Km changes with the addition of, I think it's a competitive inhibitor, you're going to see that it's a competitive inhibitor that was added. And then this is your y-intercept, and that's shown here on the equation. So if this changes, that means your Vmax changes, and that means that you have a non-competitive inhibitor added. But we'll get to that in greater detail. Did that answer any question you had, Leah? Cool. Okay. So for this, don't memorize any of the numbers. Really, she's just showing you that these are two other values that are important for measuring the efficiency of the enzyme. So like I said, your Km value is going to determine the affinity for substrate. And then your turnover number, which is your Kcat, is going to determine how quickly it can dish out product. So like I said earlier, you want a low Km value and you want a high Kcat value. So this is very fast because it's able to convert substrate into product very quickly because it's able to dish out this much product. And so lysozyme in this case would be better than chymotrypsin because lysozyme would have a higher affinity for its substrate than does chymotrypsin. And this is the same picture we saw in the last lecture, so I'm not going to go over it again. I remember there being a question on this one of these multi-substrate reactions, so I would definitely know these. So you've got two types. You've got your sequential, and then you've got your ping pong, which are on the other slide. So within the sequential displacement reactions, you've got two subtypes. You've got your ordered sequential and your random sequential. So with your ordered sequential, you're going to have it such that NHD will enter the enzyme first, followed by pyruvate. So the two substrates will enter the enzyme in that exact order where it's NADH first, followed by pyruvate. And then the enzyme is going to release lactate first, followed by NAD+. So the two products go in their respective orders every single time, and then the products will exit the enzyme in the same exact order every single time. But it's always going to be substrate before product that is released. Your second one is your random sequential mechanism. So this is where it doesn't matter what order the products enter and which order the substrates enter and which order the products leave. You can have it in one reaction where creatine enters first, followed by ATP. Then you have the exit of phosphocreatine followed by ADP. And then in the next reaction, you'll have ADP enters first, followed by creatine. And then you have maybe phosphocreatine and exits first, and then that's followed by ADP. So it's just a random reaction. But you need to make sure that you understand that the difference between random sequential and your ping pong is that it's always going to be substrates are going to enter first and then the products are released. It's just the order of the substrates that enter is different every time. And the products, the order that the products exit is also different every time, so it doesn't really matter. So with ping pong reactions, now you're having it so that you can have one product enter, one substrate enter, and then one product leave. And then you have the next substrate enter, and then the next product leaves. So essentially, it's going to be substrate, product, substrate, product. So in this case, and I wouldn't worry too much about memorizing this, these formulas, because these are just examples that she gives you, and you're going to have to learn this in greater detail later on. So I definitely wouldn't recommend memorizing this. But anyways. You should know that in this case, you have your aspartate, which enters the enzyme first. It is then going to give this amino group to the enzyme, and it's going to leave as oxaloacetate now that it's lost its amino group. And then the next substrate is going to enter. So this is alpha ketoglutarate. It's going to enter the enzyme, and it's going to take this amino group from the enzyme that was given to it by the aspartate. That's going to convert it to glutamate and allow it to exit the enzyme. So Anisha, so for this, we should know the concept and be able to recognize it with any given reaction, not just this one. Yeah, so if she were to ask it, she would ask it in a verbal kind of way. So she's not going to give you like a picture of reaction and tell you and ask you to determine like what it is. She'd probably describe it similar to how I'm describing it. I think I have like a practice question on it. I don't remember which practice exam I put it in, but yeah, so you'll see what I mean by that. She'll like describe it in a verbal way. Okay, yeah, so substrate, product, substrate, product. Okay, so don't memorize any of these drugs. I don't know why I highlighted these, but really you're going to learn about this in greater detail in pharmacology, so really don't memorize these drugs. I think the takeaway from this slide is probably the idea that if a inhibitor is going to bind to the active site. It needs to have a similar molecular structure to that of the substrate, or at least to the transition state, so that it can bind to the active site and inhibit it. So this would be for a competitive inhibitor, of course. But other than that, I wouldn't worry too much about this slide. Okay, so this is important. This is introducing the idea of competitive inhibition. So with a competitive inhibitor, you're going to see that the inhibitor will bind to the active site, and that essentially blocks the substrate from also being able to bind to the active site. Because of that, though, you can outcompete the inhibitor. So if you were to flood the solution with more of this substrate, eventually the substrate will be able to bind to all of the enzymatic active sites, and Vmax can be achieved. So you'll see that Vmax does not change, and Vmax over 2 doesn't change because of that, but you will see that it takes more time or more substrate in order to achieve the Vmax, because you need more substrate in order to outcompete it. So because of that, your Km value is going to change on the plot. Okay, so you'll see that the Km value changes because now, your slope is not as steep. And so for this line to reach half Vmax, you'll see that the Km is going to be larger. And that is essentially showing you that a larger Km means that there is a lower affinity for the substrate. I think somebody has their mic on. Okay. Okay, so this is plotting the same thing, and be able to read this graph, but also be able to read this graph as well, just in case. So this is your Lineweaver-Burke plot, and it's the same concept. So you have your Vmax right here in the y-intercept. So you're going to know that with the addition of a competitive inhibitor, your Vmax is not going to change, but your Km will. So as a result, you're still going to have both lines, the no inhibitor line and your competitive inhibitor line are both going to have the same y-intercept, but they're going to have different x-intercepts. So if you see that on the test, you'll know, you'll be able to determine which is which based on understanding which is the x-intercept and which is the y-intercept. And because Vmax and Km both dictate the slope of the line, the slope is also going to change. Yeah. Okay, so now with a non-competitive inhibitor, you're going to see that the non-competitive inhibitor will bind to an allosteric site. So it's not really going to change the substrate's affinity, for the enzyme's affinity for the substrate, because the substrate can still bind to the active site. However, because this allosteric site binding can cause the enzyme to kind of become or change conformation, it could affect the enzyme's ability to actually be functional within the active site. So you'll see that while the substrate can still bind to the enzyme with the inhibitor present, the active site is no longer functional, and you won't see the product formation. So the substrate still being able to bind tells you that your Km is not going to change. So you'll see that the Km value for each of these is the same number. But because you can't make product, your Vmax value is going to change, because you are not going to be able to increase the substrate concentration in order to outcompete it. And therefore your Vmax is going to decrease, because now you have enzymes that are essentially non-functional. So when you decrease the Vmax, you're also decreasing the Vmax over 2, and that's what kind of allows the Km to remain consistent, because it is dependent on the change in this Vmax. So -1 over Km increases with competitive. So with competitive, your Km changes, but it's going to become a larger number. So your x-intercept would get closer to 0. So yes, it would increase, because it's going from like a more negative number to a less negative number, because it would approach 0. Yeah, and I'll go back to that slide so you could see it. Oops. Yeah, so you'll see it's moving in this direction, so it's getting closer to 0. Does that answer your question, Elizabeth? Okay, so
I'm sorry, Phoebe, could you re-explain the non-competitive inhibitor graph here on the right-hand side?
the Michaelis-Menten plot, this one? Okay, so you'll see that because you have inability to form product with the addition of the non-competitive inhibitor, your Vmax is going to decrease. So you'll see that by the fact that it kind of levels out at a lower rate. So because of that, your Vmax is now at around 40, and half of 40 is now 20. So now your Vmax over 2, which is what Km essentially is equal to, that's also going to decrease, and so it's going to be able to maintain the Km at the same point for all of these. Does that make sense, Lucy?
Yes, thank you.
You're welcome. Okay, so irreversible inhibition, honestly, I don't think she'll ask about it. If anything, she'll use it as like a decoy answer. But I think it's important to kind of just have a general idea as to how they work. So she did mention this in her summary slide, so maybe memorize this substrate, but honestly, you're going to learn about acetylcholinesterase in pharm, I think. So don't worry too much about it. But anyways, with irreversible inhibition, you'll see that a substrate will bind covalently to the active site. When it binds covalently, you know that this is a strong bond, so it's unlikely to break. So because it binds there, it kind of blocks the active site from being able to participate in any other kind of reaction. So it's essentially like removing an enzyme from a reaction. So you're permanently decreasing the rate of the reaction by decreasing the amount of enzyme available for product formation. So we talked about these already. So we already talked about the inhibitors. Proteolysis we'll kind of talk a little bit more about when we talk about the blood cascade. So it's the same thing. You cleave the enzyme, and that causes it to become activated. With feedback regulation, we talked about this with purines and pyrimidines. It's the idea where you have your product going back and inhibiting a upstream enzyme. And then with covalent modification, you've mostly seen this in genetics, but not for enzymes. So it's like the equivalent of like when you like methylate the histone proteins to like, I don't remember if it opens or closes them, but same thing here, except with enzymes. So by adding a phosphate group or acetylation of the enzyme, you can activate it or inhibit it. And then allosteric effectors, which we're going to talk about next. But before that, she gives these examples of covalent modifications. So you've got your epidermal growth factors as an example of this. I don't know if this is super high yield, maybe just have an idea as to what these are, but when you learn about like signaling pathways in X block, I think it's good to understand it. Does somebody have a question? Because I think somebody has their mic on. Okay, so with these receptors, you'll see that they're kind of by themselves mostly, but like I was talking about with lipid rafts, you'll see that the receptors will kind of like float along the membrane, and when they come together by floating on their individual lipid rafts, they can get their tails close enough together for these tyrosines to phosphorylate one another. So then you have the phosphorylation of each of these tails. That is a covalent modification, and it activates this receptor when the ligands bind. Another example of this is the activation of this globular-like enzyme. So this is where you have this like protein group kind of blocking the active site. When you phosphorylate it, you're going to change the interactions of the, amino acids in this chain with the rest of the protein. So you're going to cause it to kind of change its conformation and move out of the way for the active site to be open for binding of whatever its substrate is. Maybe have an idea of this aspirin being like a covalent modification, but beyond that, I wouldn't worry too much about like these enzymes because you're going to learn about this in pharmacology. So maybe just know enzyme is a covalent modification. So when you take aspirin, essentially what it does is it works on this cyclooxygenase, or also known as COX. So the COX enzyme has this serine group that aspirin will add an acetyl group to, and essentially render it non-functional, so it's no longer able to convert arachidonic acid to prostaglandins. And that's all you really have to know for this. But really, just knowing aspirin is an example of covalent modification is good enough. Okay, so allosteric regulation. It's super important to know that these do not follow Michaelis-Menten kinetics. It's going to have a different type of graph and all of that. So the idea here is that your body undergoes allosteric regulation with the enzymes within your cells. You've got activators and you've got inhibitors. So your activators will typically bind to an allosteric site on a enzyme, and that causes a change in conformation of the enzyme's active site to allow it to be more receptive to the substrate, so it binds better. On the other hand, you have your inhibitor. So your inhibitor binds to the allosteric site. It also changes the conformation of the enzyme's active site and makes it less likely for the substrate to bind the active site. So the thing that makes it a little bit special is the idea that sometimes it works as 2 or more subunits. So similar to hemoglobin, you have your multiple subunits, you have a binding of something to the allosteric site, and then it changes the conformation of both subunits to allow substrate to bind to both, and it increases the affinity of the both subunits to the substrate. So because she talks about this specific example so many times, I would probably memorize this formula, memorize the enzyme associated with it, and then obviously remember that CTP and ATP are regulators for this reaction. Yeah. So typically don't memorize these little reactions, but this one might be important. So essentially you have carbamoyl phosphate interacting with aspartate within ATCase, which allows it to convert into N-carbamoyl aspartate. After several reactions, you'll see that the product is going to be CTP. And like most negative feedback regulators, the product is going to go back and it's going to inhibit an upstream enzyme. So what we have here is kind of the demonstration of the change of the reaction rate. So that would be with the addition of CTP, which is the inhibitor, the allosteric inhibitor. And then you also have the change of the reaction rate with the addition of substrate. So this is kind of similar to when we talked about hemoglobin, except it's talking about an enzyme that does a reaction instead of just a carrier molecule. So the same idea here. When you have a low concentration of the substrate, similar to how when you had a low concentration of oxygen, you're going to have a low affinity for the substrate. And because of that, your reaction rate is going to progress more slowly because, like I said, when I was talking about Km, when you have a low affinity for substrate, your enzyme is not going to be as efficient. And when it's less efficient, it's going to have a lower reaction rate. When you have an increase in the concentration of aspartate, this is the substrate, you'll see similar to the oxygen, you'll have a increased affinity for aspartate, and you'll see that the reaction rate will increase as well. So kind of associate affinity with reaction rate as being proportional to each other. So this is the negative inhibitor. When you have a low concentration of the negative inhibitor, the rate is going to be faster because there's not going to be a whole lot of inhibition. So your enzymes will be more efficient and the rate will be faster. When you increase the concentration of CTP, the inhibitor, you're going to see that the rate will steadily decline because now you're inhibiting more of the enzyme and you're decreasing its efficiency and ultimately decreasing the rate. So here she's just kind of showing you how it's kind of a hybrid. So allosteric regulators are kind of a hybrid of the R state and the T state. So in this case, you have your R state, which means that your affinity for the substrate is really high. So that means that the conformation of this enzyme is favorable for the attachment of aspartate. So at a low aspartate concentration, you're going to see that it's going to have a high affinity for it, and therefore the rate is going to be, rise quicker. So this would be kind of equivalent to your myoglobin curve, where it's a hyperbolic curve because it has a high affinity for it regardless of the concentration. Your T-state curve, this would be where your enzyme is at a conformation that causes it to be less receptive to aspartate. So you need more aspartate in order to get it to bind to the active site and then form products. So it would need to rely on an increasing amount of aspartate in order to change its conformation and therefore make it more receptive to forming product and increasing the rate of the reaction. So you'll see that with allosteric enzymes that are cooperative, you'll see the sigmoidal curve similar to how we saw with hemoglobin, where at a low concentration, it has a low affinity for substrate and therefore a low rate of the reaction. But as you increase the concentration of aspartate or of the substrate, you'll see that it has a higher affinity for the aspartate and it would cause an increased rate of the reaction.
Phoebe, I had a question.
Yeah.
So a couple slides back on ACTAs, I know, this one. I know the pathways involved with these examples is kind of arbitrary, but is this not, are we not looking at de novo pyrimidine synthesis here?
So it's not what we learned for de novo pyrimidine synthesis, but you will learn about this when we're talking about amino acid metabolism. So I think that's next block. But because amino acids are involved in the formation of purines and pyrimidines, they do kind of meet up with each other, the two different pathways. So I think that's what she's showing here, because they connect essentially.
Yeah, I just noticed that CTP basically inhibits CPS2, but it doesn't inhibit ACTAs in the pyrimidine pathway. So I was just kind of thrown because I thought all of these enzymes were super specific,
Yeah, I get what you're saying. Yeah, I guess it's just these little tiny differences. So yeah, CTP would inhibit the amino acid pathway that leads to it, but then it wouldn't inhibit the purine pyrimidine metabolism that leads to it. Yeah, it's weird.
It makes my brain hurt.
Yeah.
All right.
Feel that. You're welcome. Okay. I think I was here. Okay, so for your effectors, so you've got your two types of allosteric regulators. You've got your activators, which would increase the rate of the reaction, and then you've got your inhibitors, which would decrease the rate of the reaction. So in this case, ATP is going to act as an activator. So if you have an increased amount of ATP, it's going to bind to the regulatory regions on the enzyme, and it's going to change the enzyme to have a conformational change that is more receptive to binding aspartate. And because it now has a higher affinity for aspartate, it's going to increase the rate of the reaction. So you'll see that the line would move to the left. If it moves to the right, you'll see that with an inhibitor. So CTP in this case is an inhibitor of this particular enzyme. And you'll see that even with an increase in aspartate concentration, it's not going to increase as well as it would without the inhibitor. So you'll see the curve moving to the right. So kind of be able to understand the change in the curves with the addition of either a inhibitor or an activator. Okay, so what is being shown here is these L values. So you're kind of putting these two together, and they're kind of showing you these L values to show you that this is the ratio of the T state to the R state. So taut means that the enzyme is in a conformation that makes it less likely to bind the substrate. So it's got a slower reaction rate. So the taut state occurs when there is an increased amount of inhibitor. So if there's a lot of CTP, you're going to see that there's going to be more enzymes in the taut state and not as many enzymes in the relaxed state. So this L number is going to be very high because it's like a fraction, so T over R, because it's showing you the ratio of T to R. So if it's high, you know that it's more likely to be in the taut state. On the other hand, if you have an activator, you're going to see that it's going to have more of these enzymes in the relaxed state. So the relaxed state is the conformational change associated with an enzyme being more receptive to binding the substrate. So if the denominator is a bigger number, you're going to see that this number is going to be smaller. So that's why when you add ATP, your L is going to be smaller number than it would be when you add CTP, which makes it a big number. But I just wanted to clarify the L's. I don't think she's going to ask about the L values, but just in case you're confused with this graph, I gave you that explanation. But really just understanding how the curve moves is probably good enough. Okay, so this is kind of showing you like the picture version of it. So you'll see that the enzyme has a quaternary structure. I think she called it a dimer of trimers, but that's not super important. You'll see that it has 4 subunits that are the catalytic sites. So these contain the active site. Then you've got these 4 regulatory units, and these are where your allosteric inhibitors are going to bind. So either ATP or CTP would bind here, and that would, alter the conformation of these catalytic sites to make them either more receptive to binding the substrate or less receptive to binding the substrate. So that's pretty much how how it works, at the molecular level. But yeah, this is just showing you the same exact reaction, the same enzyme, the same products, and then how CTP is a product of the reaction and how it would bind to your regulatory site, change the catalytic site so it's less receptive to substrate, and then ATP would do the opposite. So I would kind of understand that. I would understand that it has 4 regulatory sites and 4 catalytic sites, and yeah, I think that's all this slide is really saying. Read through this. This was super helpful. When I took this, it kind of summarized all the main points and kind of, helped with studying. And that's it. Does anyone have any questions about these slides or this lecture before I go on to the next one?
Yeah, is the so is the negative 1 second here. Like in Lineweaver-Burke, what else is this? So the -1 over Km, is that part of the Lineweaver-Burke equation?
Yeah. Oh, wait, I know what you're asking.
The x-intercept?
So, yeah, you wouldn't find the x-intercept on the actual linear equation. It just shows the y-intercept. So, if you see an increase in the slope, that's how you'll know that the Km changes if she were to give you the slopes of each one, but I doubt she would. She would likely just show you the graph and you'd see that the x-intercept changes, and that's how you would know that a non-competitive inhibitor was added.
So does that mean the x-intercept is linear to the slope, like it will go closer to 0 as the slope increases?
Yeah, so if it gets closer to 0, yeah, it would increase the slope.
Okay.
Because it would still have to go through the same exact Vmax, so that automatically kind of shows you that it increases the slope.
Okay, cool. Sorry, I haven't had to math in a while.
No, it's okay. I feel you.
Appreciate it.
And okay, so there's a question in the chat. The chemical formulas aren't important for the last slide, correct? The last slide is showing you the same exact chemical formulas that she showed you in the, previous few slides. It's the same thing, the carmel phosphate. I would probably remember it because she does show this on like multiple slides, and understanding which are the reactants, which are the products, and for this enzyme is somewhat important because she does spend a lot of time on it. So I would probably remember it just in case. What's the answer to the question on slide 36? The answer is B. If you want me to show you how that's done, I can do that. So it's really just doing the Michaelis-Menten equation, which now I have to look up because I haven't memorized it. The next question. Wait, there's a next question.
Yes, there's one more question.
Oh, I see. Yeah. So this answer, if I remember, was D. Do you understand why?
Yes and no. I understand that DNA polymerase, because it has a larger kcat. 15, 1/15 is a larger number than 1/100. So DNA polymerase has a higher affinity for its substrate than chymotrypsin. But the wording of the answer choices, I think, threw me.
Okay, yeah. So remember that turnover number isn't really dealing with the affinity of it. So you can't really say whether the affinity changes. So that's why A is wrong. And then the velocity of chymotrypsin is greater than that of DNA polymerase. So once again, remember that this is just telling you your kcat. So by itself, it's not going to automatically tell you the velocity of the reaction because it's going to be dependent on the concentration of the substrate as well. So that's not the best answer. The velocity of chymotrypsin reaction at a particular enzyme concentration and saturating substrate level is lower than that of DNA polymerase. I think that's the opposite, right?
Yes.
And yeah, so and then E can't be right because the velocities of these two enzymes cannot be compared because chymotrypsin, okay, that's obviously wrong because remember chymotrypsin is the serine protease, so it doesn't do like a covalent anything. So you would know this is correct because remember you can change the concentration of the enzyme of the substrate in order to make it so that, because remember the formula, it goes like this and then you have your like order here. So if you change the amount of the substrate concentration, you can make it so that the velocities can be equal. So 15 times 6.7 is equal to 100. So that would even them out essentially. Does that answer your question, Elizabeth?
Where did you get that kcat times A? It's Km or the constant type. Are you using kcat and Km interchangeably?
Km is not the same thing as kcat. Kcat is just the catalytic constant, which we saw in the formula. So that's just the constant that's associated with the properties that allow it to do like the turnover number. But Km is going to be the affinity. So if this was talking about the Km, then, maybe this one would be right. But it's not. They're not the same thing.
No, I know they're not the same thing. Where did you get the equation kcat times A, which is the amount of substrate?
Okay.
But that's the rate that's not equivalent to kcat. That's a rate constant.
Oh, is it not the same thing?
No.
Oh, well. Well, regardless, you know that you can change, like if the turnover number is, if you have the turnover number being like like a general constant for each of the individual enzymes, you can alter the amount of enzyme concentration that would allow for the reaction to progress at a faster rate. So regardless, you can kind of like reason it out that way.
Okay, I guess I was thrown because the velocity, the only equation that I found was the Kcat equals Vmax over enzyme per time. So that was the only equation that I found relevant to this question, and I guess I just didn't know how to apply it, but thank you.
Yeah, but it's really, the main point she wants you to understand is that you can change the substrate concentration to change this reaction velocity. So as long as you just understand that relationship, you should be fine.
Okay, that makes more sense. Thank you.
Okay, and Alexis, did you want me to explain this question here still, or? If not, I mean, we can save it to the end because I know you guys want to start the next lecture. I'll go back to that, Alexis.
Yes.
Oh, okay, cool.
Hey, real quick on the Kcat equation, is T equal to time or total? Is it like the enzyme total? I've heard people say both, or is that the same thing? Are they both like synonymous?
Oh, I think it's over time because it's like the enzyme amount changing over time. That's what I think she said.
Okay.
So yeah, it's like because the turnover number is dependent on the time as well. So I would assume that the enzyme concentration per time.
So you actually have to multiply that by time?
No, it's just like
it's there for concentration denotation, right?
Wait, repeat that.
So the brackets there are just denoting concentration of enzyme, not that it's not that it's multiplication. You don't have to multiply to.
Right. Yeah, it's just the concentration of enzyme, and
All
then
right.
the concentration of the enzyme at a particular time.
Okay. All right. Thank you.
Cool. Okay, going back, so you're going to use the Michaelis-Menten equation, and I had my slides up that actually showed how to solve for this, but now I have no idea what happened to my actual equations. Give me a second. Okay, whatever. I'm just going to show you guys. So if you were to take the Michaelis-Menten equation, which I think it's V max, I think this is substrate concentration over Km plus the substrate concentration. Correct me if I'm wrong.
That's correct.
Okay, cool. So if you were to take Km, and we know that this substrate concentration is going to be equal to half Km, so then you're going to be V max equals 1/2 Km over Km plus 1/2 Km. Then you add those together, that's equal to 3/2 Km, and you can kind of move the Vmax out of that equation. So 1/2 divided by 3/2 is times 2/3. You canceled that, so it's 1/3 Vmax. Does that make sense? Okay, so hopefully you guys follow the math, but she's not going to ask you to do that kind of math because, like I said, she told me that she removed the like heavy algebraic stuff, so I wouldn't worry too much about it. Are we good on this lecture, or are there any more questions about it? Can you do NKM equals N over, wait, what is that? Is that part of a different equation? Miguel, like where did you get that from? Oh, like a way to solve that formula? Honestly, I don't know how to do math that well. I only know how to do it this way, so I honestly have no idea how you would do it that way. But yeah, if that works for you, you can do that. Okay, so if there's no more questions, I'm going to go on to the next lecture. This one's pretty straightforward. It's just a little bit of memorization. So okay, so for this, whole thing, you do kind of have to memorize a few pathways. So I recommend making like a sheet where you put all the information from each of these slides together in like a sequential order. Yeah, I posted a study sheet that kind of shows you how to do that. If you ran out of time and you want to see the whole thing as a whole, you can use my study sheets, but I recommend making your own. Okay, so your 4 phases of hemostasis. So this is going to allow to...
Maybe we can only see the old slides, where you don't see the new slides.
Oh, geez, okay. Thank you.
Thank you. Thank you.
Awesome, thanks. Okay, so you'll start off, you have to memorize these 4 phases because she might ask about it. So you start off with vasoconstriction. So when you have a injury to your vessel, the surrounding smooth muscle is going to kind of spasm and cause a narrowing of the vessel. So that allows for a decrease in blood loss. Your second step is going to be the binding of platelets. So the way platelets bind to the broken part of the vessel is through something called the von Willebrand factor. So this is something that is found on the collagen that is, exposed when you lose the endothelial lining of the vessel. So you've got your endothelial lining that is coming directly in contact with the blood. Below that is your connective tissue, which is made up of this collagen, and the von Willebrand factor, which is found on top of the collagen. This is different from when she discussed the negative charge of collagen activating the zymogens. So just note this to be a different thing. This is how platelets will bind to the injury on the vessel. Okay, so that's your second step. Your third step now is the zymogen activation. So this also deals with the collagen. It's what she mentioned to be the negative charge on the collagen that is activating the first factor to become active, which then triggers that cascade that we'll talk about. And the zymogen activation is important for forming the fibrin mesh. So you'll initially have all of these platelets binding. In order to kind of stabilize that and make it like a stronger kind of clot, you're going to also have this fibrin mesh that needs to kind of be intertwined with it. And then part 4 is the dissolution of the clot, because you don't want it to be there forever. Eventually your vessel is going to be healed and you're going to want to have it break apart. So this is the same thing, just like a picture of it. If you want to look at the picture, you can, but it's not important for the test. So pretty much what she wants you to know about this is that essentially the cascade is going to be done by the proteolysis of each of these factors. So you'll start off with one of these factors being activated, then that activates the next factor, and so on and so forth. So you'll see that the amount of factors towards the bottom of the pathway is going to be in higher amount than the beginning factors. So you'll see an amplification of the signal. So yeah, I'll get into the bigger details because she shows that slide like 3 more times. Don't memorize these, but understand that she's going to give you this number, the Roman numerals associated with each of these, but that they have like actual names. So as you're going through this, you can kind of associate like prothrombin, which we learn as just prothrombin as being like factor 2 and so on, but don't memorize it. A key thing to note is that whenever she kind of zooms in on a particular part of a pathway, that means she wants you to know it. So I would probably memorize this slide. So you've got an activated factor 9, And that, along with this anti-hemolytic factor, also known as factor 8, together they're going to activate factor 10. So 9 is also called the Christmas factor, and I remember memorizing both names for it, but you don't have to. And then 10 is also called the Stewart factor. So together they activate factor 10, and factor 10 is also the part of the pathway that converges the two extrinsic and intrinsic pathways. So she kind of skips down to like the last step where you have the activation of fibrinogen to fibrin. You'll see that fibrinogen in its normal form is going to be soluble. This is important because all of these factors are going to be floating around in your blood. So when it's soluble, it's able to just kind of follow your circulatory system within your blood and just float around in it. When it's activated, it becomes insoluble, which allows it to kind of bind to the surface and no longer be dissolved in your blood. So what it is made up of is these 3 polypeptide chains. You've got your alpha, you've got your beta, and you've got your gamma. So it's these things right here. So I would know what it's made up of. So the amino terminus of the alpha chain is going to have these tyrosine sulfate amino acids. So that's just like a tyrosine that's been modified. And then you've got your negatively charged amino acids that make this up. Your beta chain also has one of these amino terminus ends that are also composed of these two types of amino acids. So thrombin is going to be the factor that essentially cleaves these fibrinopeptide tails and causes it to become insoluble when it was previously soluble. So I would know most of the details in this slide, knowing that the fibrinopeptides, what they're made up of, which ones are cleaved, and then obviously knowing thrombin is the enzyme that catalyzes this. So same thing here. This is just showing you a picture of the tyrosine sulfate that gets cleaved off along with the other negatively charged amino acids. So what you're left with is this sequence here. You've got your glycine, histidine, and arginine. So you've got a kind of a mixture of positive and negative charges instead of just all being negative charges. So that allows these positive charges to essentially help this formation kind of occur. So you'll have the polymerization of all of these fibrin molecules, and so they'll assemble either head to head or they'll assemble like head to tail like this. So this is the same idea that we talked about with collagen, where they kind of form this like staggered assembly, and because it's staggered, it's going to form these striations. So it's very similar to collagen. And then just like collagen, you're going to have these cross-linking between the fibrils. So I'll show you. The cross-linking would occur like between the different molecules, and that's what's going to allow it to increase in stability. So it's very similar to how collagen is formed. I would know which 2 amino acids are associated with this. So glutamine from one fibrin would then associate with the lysine of another fibrin molecule, and through transglutaminase, or she could use factor 13A. So I would maybe know these as one and the same because she mentions either one. I would know that they go through transglutaminase to form these cross links, but the structures you don't really have to worry about too much. And so you'll start off with a fibrin monomer, which then becomes a dimer, which then becomes a protofibril. And then this is where she talks about factor 13A, which is that transglutaminase, which is forming the cross links that allow for this stability to occur. So that's like step 4. Okay, so the thing I have boxed off is like the most important part of this pathway. That I would probably memorize if I were you. She showed you this in that first slide that I pointed out, so you kind of need to know this. I would say that the tissue factor aspect of it and like this, I wouldn't really worry too much about, but I would at least know that it's the tissue factor that is going to activate the extrinsic pathway. So the difference between the two is pretty much based on the kind of injury that you get. So the intrinsic pathway is going to be activated, and it uses all of the factors that are already within the circulatory system. Oh, Lexia has a question. Do we need to know any of the structures? No, don't worry about any of the structures for any of these, except for your amino acids. You have to know your amino acids, but for like every other type of pathway, don't worry about structures. Okay, so your intrinsic pathway is going to be activated by whatever factors are present in your bloodstream. So if these factors come in contact with the collagen, so if you lose one of these endothelial cells, you'll kind of expose this connective tissue below it, and that's filled with this collagen that has these negative charges, and the negative charges are going to activate the the factors, the zymogens that are associated with this cascade. That's not to be confused with the von Willebrand factor, which is what allows the platelets to bind. So this isn't talking about platelets. This is talking about the zymogen activation. Okay, so on the other hand, if your tissue surrounding the vessel is damaged along with the vessel, you'll have the activation of the extrinsic pathway. So this tissue factor would be secreted by the surrounding tissue, so it's not within the vessel. And if there's like a hole in the vessel, the tissue factor can seep in and activate the cascade that way. So I would just kind of know that tissue factor does the extrinsic pathway, but beyond that, I wouldn't worry about any of these other molecules. What you do need to know is what I've boxed here that we talk about in the next several slides. So for prothrombin to become activated, you start off with the prothrombin molecule, and it has this pro sequence that is pretty important. So what happens here is you have your pro sequence that contains this gamma carboxyglutamate. So these are these little receptors here. At the same time, your platelets are going to be secreting calcium, because when platelets are activated, they just start releasing a ton of calcium. That's like their thing. And so because the platelet membrane has a lot of phospholipids on the membrane, these are going to be negatively charged. And so the calcium, some of the calcium is going to stick to the negative charges on the phospholipids on the membrane. And so from there, you're going to have this gamma carboxyglutamate, associate with the calcium. And that allows this whole prothrombin to kind of bind to the membrane of the platelet. So because it binds to the membrane of the platelet, it brings the prothrombin close enough to these other factors that are bound to the membrane of the platelet, factor 5 and factor 10. And factor 5 and factor 10 both kind of work together to do the cleaving here and the cleaving here. So it's important to understand that the active aspect of thrombin, which is both of these subunits, are held together by disulfide bonds. I would know that. And then, the pro sequence will continue to stick onto the membrane, but the thrombin, the active aspect of the molecule, is then, secreted, and it floats down into the bloodstream to do whatever it has to do next. I think there is a question on the exam about this prothrombinase complex, so I would memorize these 4 factors that are associated with it. And then kind of knowing this, whole sequence of events is also important.
Hey, Phoebe?
Yeah.
So just if you could go back to the last slide.
Yeah.
So just to kind of walk back through that again. So the prothrombin will attach to the membrane first before any cleaving happens.
Correct.
Then it attaches with these like calcium pieces or calcium molecules to the membrane. And then the cofactors are on the membrane already? Is that how it is?
So yeah, these cofactors also have these gamma carboxyglutamate things. So they're already stuck to the membrane, like they're just hanging out there. But it's it's the platelet that's secreting calcium, and it's just the calcium just happens to interact with the phospholipids on the membrane. So there's a bunch of calcium hanging out here, and it's going to be the gamma carboxyglutamate, which is on the prothrombin, and together they bind onto the calcium. So it's the calcium's there already. This whole sequence binds, and then there's the cleavage.
Okay, and then that thrombin will go where it needs to go next.
Yes.
Got it. All right, thank you.
You're welcome. Okay, so this is just showing you how the gamma carboxyglutamate, which is this, associates with the calcium on the phospholipid membrane. I wouldn't worry about the chemistry of this. I wouldn't know any of these like structures. Just understand that carboxyglutamate associates with the calcium. I would say that knowing the precursor for gamma carboxyglutamate was something that I memorized my year, but I wouldn't say like it's super important compared to understanding that vitamin K is kind of like a cofactor that is associated with the conversion of glutamate into gamma carboxyglutamate. So if you don't have vitamin K, you're going to lack gamma carboxyglutamate, and that's going to prevent the prothrombin from binding to the platelets, which ultimately prevents its activation. So there are a lot of medications that are important for inhibiting the clotting of blood. So some of these, and I would memorize these two at least, are dicumarol and warfarin. So both of these have structures that are very similar to vitamin K. So if you were to take these, they would kind of replace vitamin K in acting as a cofactor for this conversion of glutamate to gamma carboxyglutamate. And because it's not exactly perfect, it's not going to work like vitamin K would. So then it would prevent ultimately prevent the cleavage of the prothrombin to thrombin, because it can no longer bind to the platelet surface because it's missing the gamma carboxyglutamate. But as for like all of this, just knowing that vitamin K is important for it and that warfarin and dicumarol inhibit that event is probably good enough. All of this is like too much information, so don't worry about that. So heparin. So heparin, if you've ever, if you know anybody who takes heparin, this is a drug, but it's also something that your body makes naturally. So what it is, it's just like a sugar that will help with the formation of the thrombin-antithrombin complex. Don't worry about the structures, anything here. It's just kind of like an introductory slide. She pretty much skipped this slide, so don't even look at it. So this is pretty much what heparin is. So it's a bunch of sugars. All of them have negative charges. So it's this chain of sugars. So essentially what it does is it's negative charges interact with the positive charges on the thrombin, and then as it's kind of floating around in your blood, it'll bind to the thrombin, and then later it will probably bounce into the antithrombin because it also has these positive charges that it associates with. So because now both thrombin and antithrombin are on the same chain of heparin, they're more likely to bump into each other and bind. So what antithrombin does is essentially it inhibits thrombin from functioning, and without thrombin, you're unable to activate fibrin. So it prevents blood clotting. Same slide again. Okay, so TPA. The last step of, the formation of fibrin clots is the dissolution of fibrin clots. So this happens after your vessel has already repaired itself. And so it's important to break up these clots so that they don't obstruct the blood vessel. So you have plasminogen that gets converted to plasmin for this step. So plasmin is super important to understand, but you need to know that TPA is the enzyme that, converts it to plasmin. So Some of you have probably heard of TPA if you've ever worked in the ER or in neurology. It is what they give stroke patients if they've had a stroke within a certain amount of time, and they give it to them so that it can break up the clot. So this is exactly what it does here. This is TPA. This is going to kind of show you the amino acid sequence of TPA. You've got these Kringle domains, so this is important to understand. Like, this is pretty high yield, is understanding what the Kringle domains are. These are going to be regions of the protein that allows TPA to bind to the clot. So it will have like amino acids that are favorable for binding to certain amino acids on the fibrin exterior. So the serine protease on the TPA is going to be the actual functional aspect of it. So like we talked about serine proteases in the past, such as chymotrypsin or trypsin, same idea here. It's going to bind to the clot, it's going to weasel its way into the clot, and then it's going to find plasminogen, which is already associated within the clot, because when you have a blood clot, it just has all the factors kind of, woven into the actual like whole fibrin clot. And so TPA is then going to find the plasminogen, it's going to cleave it using the serine protease, and then it's going to activate plasmin so that it can go and dissolve the fibrin. And so then you have the degradation of the blood clot. And this is just showing you a picture of that. And then for this, literally just know hemophilia. Hemophilia A is the most common one, so if she asks about it, that's what she's going to ask about. And the only thing I would know is that it's a mutation in factor VIII. But for this slide, she kind of mentioned, that there are two types of disorders. You've got your bleeding disorders, so you have excessive bleeding with these, or your excessive clot formation with certain types of disorders. So essentially what your body's doing at all times is balancing between your bleeding and your thrombotic state. So the amount of factors that you have in your blood right now are likely going to tip the balance towards the anti-clotting conditions. And then if you cut yourself, then it would tip the balance towards clotting conditions. And then, these disorders are when the balance is already tipped due to some kind of mutation, and that, induces either excessive bleeding or an excessive thrombosis. And I just noticed there's a question in the chat. What's the purpose of cleaving between 323, 324 if we want those two segments together anyways? Are you talking about thrombin?
Yeah, it's all the way back at thrombin. If you want to answer it at the end of the lecture, though, that's fine.
Oh, it's okay. I'll just answer it now. I don't know. I think we just happen to evolve that way. So sometimes evolution isn't perfect. So you wind up with something that still works, but it's not ideal. I guess we're just lucky that we have those two disulfide bonds that hold it together so that it's still functional. But really, I just don't think there's a purpose to it. It just happened to occur.
Okay, thank you.
No problem. Oh, and that's it. Yeah. So read the summary, do the practice problems. Yeah, that's it. Does anyone have any other questions on the clotting?
Yeah, so seeing that this is probably one of the more clinically significant PowerPoints we've seen, I could definitely see vignette questions coming that would probably kind of, like you said, if you worked in the ER and stuff that's probably an advantage. That'll probably help me in this case, but I still feel like I'm kind of confused on basically, because you're looking at aspirins and they're platelets, right? And then you got heparin, which is an anticoagulant, and then TPA is essentially a clot buster. But in layman biochemistry terms, what really is the difference between the anticoagulants and the antiplatelets? I mean, I know there's a lot of pathways involved, but if you could sum that up simply. Simplify that would help me a lot.
Yeah, so aspirin you said was antiplatelets, and we don't have to know about aspirin because right now we're just talking about the zymogen pathway, which this slide no, just kidding, it's the first slide. So the first slide kind of shows you, the 3 steps in, blood clots. So the second step that's super important is the formation of platelets. So the platelets are the first to kind of realize like that there's a, vessel injury. So that's what aspirin would go to. But because we learned hemostasis like 3 more times, like in physiology, pharmacology, and then again in pathology, she's just kind of giving you this like more so focused introduction to the zymogen activation. So it's really the heparin and the warfarin that are associated with inhibiting the zymogen activation versus aspirin, which you'll learn about like later on, more so focusing on the platelet activation part of it. So if you inhibit either of these, it's going to inhibit the ability to form a clot because you need both of these steps in order to allow that to happen. Does that kind of answer your question?
Yeah, that helps. And then you said, so like heparin, it pretty much just I guess I'm still kind of confused on heparin.
Yeah, it's okay. So it would essentially kind of inhibit this part of it because it's going to kind of allow for thrombin to associate with antithrombin. So antithrombin is a inhibitor of thrombin. So if you stop the coagulation cascade at thrombin, then you can't get fibrinogen activated to fibrin. So then you wouldn't have like the formation of fibrin, which is the whole point of the blood clotting cascade.
Okay, so those kind of work earlier in the pathway, and then they kind of like they affect fibrin, which affects anticoagulants.
Right, exactly.
Okay, cool. All right, thank you.
You're welcome. Another question in the chat. I know with the membrane and ROS PowerPoint, Dr. Patel stated that the content is weighted equally despite differences in PowerPoint length. In general, are all the lectures weighted equally, or are there going to be more questions coming from particular? So yes, all of the PowerPoints are weighted equally. She even told me 2 days ago that even the ROS lecture, which is very short but also part of the membrane lecture, that is going to be weighted equally with the membrane lecture. So essentially, we have 10 different lectures if we add the ROS to it. So that's going to be 5 questions per lecture. So I would expect to receive 5 questions per lecture. I know that's not what you really want to hear, but I would say from what I remember, it was pretty even with the amount of questions per lecture. And then did that answer your question? I don't remember who asked that. Can't like scroll up, whatever. Hopefully that answered your question. Okay, yes, Abigail, I can go over the self-assessment questions. So the blood clotting cascade are controlled by, so the cascades, note that this is specifically zymogen activation, right? Because you're going to have the cleavage of one factor to activate the next factor and so on and so forth. So I believe it's zymogen activation because you're not really going to see a whole lot of phosphorylation. There's no allosteric activation. So it's zymogen activation when you think of the blood clotting cascade. For number 2, which of the following statements is true of vitamin K? So remember that vitamin K is going to allow for the formation of the gamma carboxyglutamate. Obviously, it's not going to reduce antithrombin levels because those two things aren't related. And then low levels are observed in patients with liver disease. That's not even relevant to what we're talking about. But remember that with warfarin is kind of like an antagonist of vitamin K. So if you were to overdose on warfarin, the literal treatment for it is to overdose on vitamin K because then vitamin K can outcompete the warfarin and, you can go back to normal clotting levels. So know that they compete with each other. Yeah. And then which of the following proteins are administered after heart attacks to increase survival odds? So this is like what I talked about with like the stroke patients, but it also works with anything that has to do with like a blood clot. So stroke, heart attack, that sort of thing, you're going to have TPA. And I know she didn't really talk about this. So really the only reason you would know the answers to these questions are if you have like some kind of clinical experience associated with it. So I feel like this is unfair. I will say that having clinical experience does really help with like the test questions in general, which is kind of unfair to people who haven't had clinical experience. But honestly, I mean, for all of the classes, it really does help with certain terminology and all of that. But I doubt she'll ask something like this because she didn't really talk about TPA as like a, thing for heart attacks or strokes. Hopefully that answered your questions, Abigail. And then Lexia, since she refers to the pathways with Roman numerals, she won't expect us to know them by name. So yeah, I would probably memorize the Roman numerals over the ones that aren't Roman numerals. There's a few exceptions to that because she does have both names, like in some of the pathways. I think like anti-hemolytic factor she used instead of factor 8, I think. So for some of them, I think it might be beneficial to know both. But only if they're both written on the slide. So anti-hemolytic factor would be an example of that. And, you know that that's associated with, hemophilia because that's factor 8. So you can remember it that way. But for the most part, she does like using Roman numerals over, the actual names. And to answer your questions, Srihar, hopefully I pronounced your name correctly. I am waiting for Dr. Patel to give me the go-ahead because she's reviewing my practice exam. So I have to pretty much send her every practice question I make for her to approve before I can post it. This is mostly to minimize any questions being too similar to exam questions. So as soon as she, replies to my email, I sent it to her yesterday at noon. So hopefully she'll get back to me by the end of the day, but I'll post it as soon as I am given permission to. Are there any other questions about either of these, lectures?
I had a quick question.
Yeah.
I know Ivy said for genetics that Dr. Blank's end of lecture questions were kind of fair game to show up on exams. Would you say that's the same case for her self-assessment questions or not really?
So not really. I know Dr. Blank, doing the fill in the blanks are super helpful because he does use the exact questions sometimes. And for, not immuno because Eugen doesn't do it anymore, but, for biochem, I wouldn't really say they use the same questions. They may use similar questions, maybe worded a little bit differently, but, focusing on the same concepts. But no, she doesn't like repeat the questions from the self-assessment the way Dr. Blank does.
Okay, thank you.
You're welcome.
I have another question, Phoebe. Sorry, I know I've been peppering you lately. With
No, it's okay. You're good.
So number 2 in the self-assessment. So just kind of piggybacking on what we were talking about earlier. Say like you had excessive aspirin activity, would vitamin K still be given to treat that, or could that work?
No, because like aspirin specifically works on the platelets. So this is like a different pathway. So the platelet pathway, don't even like worry about it. Don't worry about aspirin. Like they're separate things because that's like the second step of hemostasis. This lecture is really just focusing on the third step, which is the zymogen activation. Okay. So yeah, because vitamin K is specific for, doing the gamma carboxy glutamate, for the binding of prothrombin onto the platelet.
Yes.
But yeah, warfarin is really just an antagonist for vitamin K specifically.
Okay, cool. All right, thanks again so much. I appreciate it.
You're welcome. Any other questions, guys? I do have a Kahoot. It's like 6 questions long. So it's going to be brief. I literally ran out of questions because I was making the practice exam and all of that. So sorry if it's brief. We can play it now, though. I don't know if you guys can see my screen. Probably not.
Not yet.
Okay.
Phoebe, when are you going to post your practice exam?
As soon as Dr. Patel gets back to me and gives me permission to post it, because she's reviewing it right now, Hopefully she gets back to me by the end of the day because I do want to post it as soon as possible. So it's really up to her. I'm sorry if this has been an inconvenience to you guys. I'll try to like work on it faster and send it to her sooner so that this doesn't happen again. So I apologize.
No worries. I know she's trying to review, so it's kind of like out of your hands at this point. So.
Yeah.
But thank you.
You're welcome. I'll give you guys like one more minute to join in case anybody's having any issues. Okay, I'm gonna start. Right, yes. So it's factor 10A, not factor 9A. So make sure you know the prothrombinase complex. Okay, so this is kind of a little bit of a trick question. She did include this in her summary slide, so make sure you read the summaries because sometimes she'll include things that she doesn't like really talk about in lecture. And I think I remember at least one time where she asked a question based on something on the summary that she didn't really harp on during lecture. So make sure you know this. So it's transglutaminase because that is a kind of a procoagulant. These three are the ones listed in her summary. So make sure to read the summary slides for all of the lectures. And hemostasis is just talking about like anticoagulation. Cool, yes. Remember, vitamin K is a procoagulant, and then warfarin is its antagonist, so it would do the opposite of vitamin K. So know that vitamin K isn't procoagulant, not an anticoagulant. Cool, yes. So this is a zero order reaction, so it is going to be independent of the concentration of the substrate. Yep. Remember that the KCAT is only talking about the turnover rate. It has nothing to do with the affinity. Km is talking about the affinity. So when you have a decrease in Km, there's going to be more buildup than breakdown. So you're going to have a higher affinity when it's a low number. Yep, so this is your ordered sequential mechanism. This is kind of how she would probably like describe it to you guys. She won't show you an actual reaction that does this, but she'll describe it to you guys. So when it's an ordered one, you're always going to have the same exact order of substrates entering and the same exact order of products leaving every single time. So make sure you know the difference between all of these. Congrats to whoever is vitamin K. Nice job. So you guys are free to leave. If anyone has any more questions, I'll stick around for a little bit. But if not, I'll see you guys later at the Q&A session, just not in person because I'm still quarantining. You're welcome.
Hey Phoebe.
Yeah.
I have a question. Could you go over on the first lecture, could you briefly go over the multi-substrate reaction again? From like the last question we literally did, the ordered one on the Kahoot.
Right, yeah. You want just the ordered sequential mechanism?
Yeah, and how you said how it wasn't the importance to differentiate between the random sequential and the ping pong.
Okay, yeah, okay. So for ordered can you see my screen, by the way?
Sorry, yeah, I can see it.
Okay, cool. So for the ordered sequential mechanism, you're always going to have, like in this example, where NADH binds first, then pyruvate binds, then a lactate is released, followed by NAD+, and then in the next reaction, you're going to have NADH binding first, pyruvate binding next, then lactate, then NAD+, and it's the same order over and over and over again. For the random sequential, you're going to have either creatine or ATP binding first, so it doesn't matter which one binds first. And it also doesn't matter which one is released first. So sometimes ADP will be released before phosphocreatine. Other times phosphocreatine will be released before ADP. But the difference between these two and the ping pong is that your substrates are both going to bind first, and then your products are both going to be released after that. Whereas your ping pong mechanism is going to be where your substrate binds, then your product is released, then your substrate binds, then your product is released. So it's going to be in like a substrate product kind of, like a mechanism. But yeah, so for the ping pong reactions, I believe it's going to be the same substrate is always going to bind first, followed by the same product being released first, followed by the next substrate always being second, followed by the next product always being second. Does that kind of clear up any issues you were having with that?
Yeah, that makes a lot more sense. Thank you.
Okay, great. Awesome. Any other questions, guys?
I have a question, Phoebe. I think someone had asked this before, but I just forgot what you had said. Your one-page study sheets that you have uploaded, do you think like those are enough for, like, it contains all the things that we would most likely see on the test? Like, let's say if I base my notes off of that and stuff, like, you think I would be in good shape?
So, okay, that's kind of a hard question to answer because I really, really, really do recommend memorizing everything, learning everything, because you never know. But I will say that my one-page notes do have the bulk of the material. They have the high yield stuff. I don't want to tell you to just, not even bother looking at the PowerPoints and just look at my one-page notes because I will probably be leading you astray by telling you to do that. So please don't do that. But if you kind of want to see everything kind of put together, all the main points put together, I would use them for that reason. But yeah, like I said, I really think like memorizing, being able to go through the slides and being able to explain each individual slide will put you in a very good shape versus just, being able to explain the one-page notes that I made. Like a lot of those notes are based on my notes from last year, which were more something that I used like as a supplementary type of thing. So I've never just focused on my one-page notes and not looked at like the PowerPoint details. So yeah, I honestly, like, I wouldn't say don't worry about the PowerPoints. I would say kind of focus on that material, learn that material based on what's on the slides for the material I have in my OneNotes, but don't just rely on my one-page notes. Does that answer your question kind of?
Yes, it does. I've been looking at everything, like not just your one-page notes. So I just wanted to be certain, like, what your one-page notes were good for. So thank you.
Oh, gotcha. Yeah. So most of those are just to kind of look at a zoomed out type of broad, visual of like all the major points.
That makes sense. Thank you.
You're welcome. Any other questions, guys? I'll probably stick around for like maybe 2 more minutes.
Phoebe, can you go over the dissolution of fibrin clots again?
Yeah. So the TPA thing. Is it this slide?
Yes.
Okay. Yeah. So TPA is the enzyme. It's also called plasminogen activator. That's what the PA stands for. But TPA is the enzyme that activates plasmin. So it takes the plasminogen, it cleaves off plasminogen's propeptide, which is just like all the other zymogens, how it has a propeptide that gets cleaved